Hi, everybody, and welcome back to MTED 110. Today is lecture 6B. We're going to finish chapter 6. This one's going to be a little bit long, in part because we're starting with a video, and the video is about 6 minutes long. So let's go ahead and get started. All right, so we left off here, and what we're going to do today is we're going to make sense of fractions and algorithms, and then we're going to talk about decimals and percents, in particular, like repeating decimals and things like that. But first, I want to watch this video of a student, Rachel, demonstrating how important it is to make sense of fractions. So let me go ahead and pull up the video really quick. Okay, let's see here. Oh, 1 second here. It's kind of a... There we go. Okay. There we go. Okay. So yeah, let's just watch this. And again, you can follow along if you just click the link on the slide and you want to watch this in a different format, you can. Just click the link and it'll take you to the video. But we're going to play it and watch it right here. I might pause and make some comments too as we go along.
Really, in the traditional lesson, they were just focusing on the algorithm, on the operations. And in fact, that's what we prompted them with, or what operations do you need to do? It didn't have that much to do with fractions. I mean, we could have done the entire lesson without even having fractions, except that, so really just on the dividing and multiplying and adding. Without a whole lot of understanding of why they're doing it. I don't think it was ever discussed why they were doing that at all. And I think some of my students were probably wondering, why are we doing this? But they were following along in a good traditional lesson.
You're being good
Don't
students.
ask any questions, just don't ask why, just invert and multiply. Okay.
Just a quick note, that whole don't ask why, just invert and multiply, that was something that I was told as a child when I was learning about fractions. So, for example, when you divide by a fraction, why do you flip and then multiply? Why do you do that? Why, who says that you're supposed to do that? Why does that work? That was never explained to me. I was just told, don't ask why, just invert and multiply because it works. Just because, right? Anyway, let's continue.
This time I'm going to ask you to change this into an improper fraction.
Okay. We did this before, but I don't exactly remember it as well because I didn't figure it out for myself.
Tell me about that. What do you mean you didn't figure it out for yourself?
Well, when she tells us the answer to something, and I try and find out how she got it, and so when I figure that out, it's easier, and once I figure it out, it stays there because I was the one who brought it there. So, and it's just easier to do when you figure it out yourself instead of having teachers telling you.
Is that?
Yeah, so this is another important point about teaching, and this is why you have to let students struggle and go through that tension and discomfort that we were talking about back in the very, very first lecture, right? You remember things more when you figure them out yourself and when you make sense of them on your own. So if a teacher just gives you all the answers and said, here's the answer, and here's how you do it, and here's how you do this, and here's the answer, you don't really retain that knowledge very much. And this is a student who's cognitive enough and aware enough, I should say cognizant and aware enough to recognize that she learns better that way. Let's hear what else she has to say.
How she usually does it, or?
Yeah, and then this little time it was different and it was harder.
So what she's saying here is that she doesn't quite remember how to convert this to a mixed number because this was one of those situations, or this is one of the very few times that her teacher just kind of gave them the answer. And so she can't really remember it. She can't really remember exactly how it works. Yeah.
I'd say that when students create their own algorithms, it is something that they keep forever. If they can see the idea of going from improper to mixed, and they know what they're supposed to do, and they see that they are able to conceptualize it, then they're able to come up with a method. They can come up with their own method to do it.
How about if we do a mixed number and change it into an improper fraction.
Oops. Okay. Now the way that I was taught was times 3, which would be 9 plus 8 equals 17, so it'd be 17 eighths. Or really, you could just do, you knew that there was 8 holes, so there had to be like 1, 3, 1, 2, 3, 4, 5, 6, 7, 8, and then there was 3 of these, so there had to be a, then there was 3 left, 3 of these, 1, 1, 2, 3, and then there's 8 in each, and then there was 3 more. 1, 2, 3 out of the other holes, and then you just kind of it has to be 3 times 3 because there's 3 holes, so it has to be 3 right here, 3 right here, or 8 right here, 8 right here, and 8 right here. Three, 8. Let me try this again. Okay. There's,
How many do you have here?
that's 8.
And how many do you have here?
8.
And how many do you have here?
8 and 3 left over.
So how much is that altogether?
27.
27 what?
Eighths.
Okay. So you have 17 eighths here. Which one do you think is correct?
I'd say this one.
Why don't you write it down? What you just told me there was how many?
24 eighths.
And that's not what you said before.
27.
27. Okay.
That's 10 more than 17.
Okay.
9.
Why don't you look up here? Remember you were saying you needed to multiply something and then add something? Is there a way that you can multiply something here and then add something and come up with 27?
You could multiply this and add the denominator.
Okay, and would that make sense to do that?
Yeah, because
Why?
8 is 1 hole and there's 3 holes. So there has to be 8 times 3, which is 24. Then you have to add the remainders.
Okay. So which one do you think is right?
This one, 27 eighths.
Okay. I am still a little tiny bit curious. When I showed you this time, you still wanted to go to the rule.
1 second here. I lost track of the number she was computing. Was it 3 and... Come back here. Oh, 3 and 3/8. My bad. I was saying 5/8. Okay, let me go back up here. There we go. My bad.
This one, 27 eighths.
Okay. I am still a little tiny bit curious. When I showed you this time, you still wanted to go to the rule, even though you didn't quite remember it the right way. Why do you think you do that?
Well, because I was taught that first,
So do you think
and I kind of compared.
if you had your choice of which lesson you could have learned first, which one would you have liked to have learned first?
This one, because I would have remembered how to do it the right way, the correct way.
Okay. So you think this one gets in your way sometimes?
Yeah.
I see. All right.
Boom, and there it is. Oh, wait, just disappeared on me. Yeah, okay, so let me go back to the slides here. Yeah, that's really amazing. So you can see in that video that she tried to do the algorithm first, right? So she basically was doing this first, and she was like, okay, well, I'm supposed to multiply and then add, and she was getting the wrong answer, right? She got 17 eighths, because I think what she did first was she multiplied these to get 9, and then she added this to get 17. She had 17 eighths, right? And then she was like, sure, that's got to be the answer. And what was amazing is she then went through and started using these pictures right here. She used these pictures to explain that it had to be that many eighths. So she made a whole bunch of holes, a whole bunch of units, cut them into 8 equal sized pieces. And then she started counting them and she was like, wait a minute, that's more than 17 already, but I got 17. And then she goes back and explains like, oh, she tried that algorithm, but she couldn't remember it. She couldn't remember the algorithm correctly. And so the interviewer there, the teacher, was like, so, why do you do that? Why do you think you do that? And she's like, oh, well, that was what she taught me first. And so I think I just go to that, on my own. And she then at the end, she said this way would be easier because she would remember how to do it the correct way. So this is a student who's flat out telling us as educators that she prefers to learn the model before she learns the algorithm. So if you don't believe me, you got to believe these students, right? These students will let you know that it helps them a lot. Anyway, so I just think that video is really great, and I think it's a good motivator for this entire module, actually. Okay, so moving on, let's talk about comparing fractions. This touches on the very first question we asked at the beginning of this chapter, where I was like, oh, can you tell which number is bigger? It was like 3/5 and 17/30 or something like that, right? So the way that we can get a feel and get a handle on the size of fractions is using benchmarks. We did the same thing when we were first learning about whole numbers and stuff. We talked about benchmarks like 10 and 5 and stuff like that, and our numeration system, right? We can do the same thing here with fractions. So some handy benchmarks are these. Keep these benchmarks in mind at all times. 0, 1/4, 1/3, 1/2, 2/3, 3/4, and 1. And they're written in ascending order too. So these are the benchmarks that you want to compare everything to because these are nice, easy to visualize benchmark fractions. So let's try this. Let's take a moment and I want you to think about this and try to compute these. So think for a minute and then try to put these in order. But I want to emphasize, do not use a calculator. Do not use a calculator and don't try to write them don't find a common denominator. Don't find a common denominator. Okay? So think about it for a minute. All right, now try to write something down. All right, now let's do these ones together. So we're just trying to order, we'll do the first set, okay? We're just trying to order those from least to greatest. So we have to find the smallest one of those numbers and the biggest one of those numbers, and then the middle, the middle number, right? So how can we do this? Well, let's look at our benchmarks again. Remember these benchmarks. All of these numbers are pretty close to 1, I would say. Notice that this is 1/7 away from 1. This is 1/8 away from 1. And this is 2/9 away from 2/9 away from 1, right? So what we're going to do is we're going to try to visualize this on a number line and see if we can see how far away these things are. Okay, so let me draw a number line here. Oh, that's too thick. Make that a little thinner. Yeah, it's still a little bit too thick. Maybe this. That's better. Okay, so let's draw a number line. And here's 0, and here's 1, okay? And let's see, let's look at 6/7 first. So 6/7 is 1/7 away from 1, right? If I add a seventh to that, then I get 7/7, which is 1. So 6/7 is 1/7 away from 1, okay? Now let's look at 7/8. 7/8 is 1/8 away from 1. So if you add 1/8 to 7/8, you get 8/8, which is 1. So it's 1/8 away from 1. And my question is this, which is bigger, a seventh or an eighth? Which is bigger, a seventh or an eighth? Think about it for a minute. All right, now let's talk about it. So 1/7 is going to be a bigger number. And how can you tell? Well, let's use a pizza, for example, right? Here's my pizza. Delicious. Now, if I cut that into 8 pieces, my pieces, equal size pieces, they'll look something like that. But if I cut it into 7 pieces, well, I'm going to have one fewer pieces. So the pieces are going to be bigger. The pieces are going to be bigger, which means if I cut this into 7 equal size pieces, which I don't know how to do, this is actually one of the reasons why circles aren't the best, right? Circles aren't the best. Sometimes rectangles are much easier to deal with. But the idea here is that if I'm cutting it into 7 equal size pieces, I'm going to get more pizza that way, right? Each slice is bigger. Sorry, that's a 7. There you go. Each slice is a 7th of the pizza, so they're bigger than if I were to cut it into 8 pieces. So if I cut it into 8 pieces, the pieces are smaller. So in particular, we can reason that 1/8 is smaller than 1/7. And because of that, 7/8 has to be bigger than 6/7, because 6/7 is 1/7 away, right? 6/7 is 1/7 away from 1, but 7/8 is only 1/8 away from 1. So 7/8 has to be like right here somewhere. And this distance is 1/8, right? So there we go. Now we've already got that. So the next thing we have to do is we have to think about this other number, 7/9. Okay, 7/9. How can we figure that out? Well, 7/9 is 2/9 away from 1. But does that really help? It's kind of hard because we're trying to basically figure out where to put 2/9 in all of this. Hmm. 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 What could we do? 7/9. Well, that's 2/9 away from 1, but 7/9 is also, well, let's look at these two numbers. Look at 7/9 and 7/8. Well, 7/9, if I cut a pizza into 9 pieces and I take 7 of them, I'm going to have less pizza than if I take 7/8 and cut or if I take a pizza and cut it into 8 pieces and take 7 of those, right? So if I cut the pizza into 9 pieces right here and I take 7 of them, well, the pieces are kind of small, right? I can get 9 of them out of a pizza. Here I'm getting 8 of them out of a pizza. So that tells us that 7/9 has to be smaller than 7/8, right? Because 8s are bigger than 9s. 8s are bigger than 9s, right? 1/9. So that tells us right away. Wait, I just lost my train of thought. That tells us right away that 7/9 is going to be small. Yeah, small. 7/9 is going to be smaller than 7/8, right? So 7/9 either goes here or it goes here. The question is which way? Which does it go on either side? Does it go in the middle or does it go on the other side? What do you think? 7/9. So now we need to try to compare these. 7/9 and 6/7. What could we do? Well, let's see here for a minute. Hmm. Hmm. Well, let's think about 6/9 instead. Now, 6/9 is 2/3, and 6/9 is definitely smaller than 7/9. But how do we compare 6/9 and 6/7? 6/7 is definitely bigger than 6/9, right? It's definitely bigger than 6/9. Oh, sorry, I have that backward. 6/7 is definitely bigger than 6/9. Okay, so that means over here, this has got to be 6/9. 6/9 is somewhere down here. So what about 7/9? What do you think? What could we do here? What do you think? We're just trying to reason about sizes of things, right? So if that's 6/9, then 7/9 is going to be right around there. So 7/9 goes right before 6/7, right? But are we sure that it doesn't go in between? How can we be absolutely sure? What could we do? How can we manage these sizes? Let me think about it for a minute. 6/9, 7/9, 6/7. Well, I guess I would say this. 6/9 or 7/9 is 1/9 away from 6/9. And what I really need to know is if this distance here between 6/9 and 6/7 is bigger or smaller than a ninth. Bigger or smaller than 1/9. what do we think? Well, if I add 1/9, where do I end up? Hmm. Where are you, 7/9? Hmm. Where did you go? Are you on this side or are you on that side? Huh. I wonder. Hmm. Well, up here I was saying this, right? 1/9 is smaller than an eighth, and it's definitely smaller than a seventh. And I'm pretty sure that this is going to be, oh yeah, so that's definitely going to be small. Yeah, so it's got to be right there. Yeah, so this has to be our 7/9. Our 7/9 has to go on this size, or I'm sorry, on this side. Once you start comparing these sizes right here. All right, that's one way to do it. There are other ways to do it too, and maybe you actually thought of some while I was sitting there ruminating and thinking about it. But let's try to do the next one also. Okay, let me delete these. Ah, delete. Okay. All right, so now let's look at this one right here. And we're going to use a similar argument, right? So we need to put these, we need to order these from smallest to largest. So let's go ahead and try this one together. The first thing I notice is that 20 or 40 is 2 times 20. So 7/20ths is the same thing as 14/40ths, equivalent fractions, which we'll talk about in a minute here. So that means that it definitely goes in this order, 13/40ths, and then 14/40ths. And then what about this one? 8/24ths. Maybe reducing it could help or something like that. Let's see, 8/24ths is 4/12ths, which is 1/3. So this is 1/3. 8/24ths is equal to 1/3. That's interesting. Maybe if we can somehow compare this to a third, it'll help us out. So let's try this. Okay. Let's look at 7/20ths again. If the denominator was a 21, that would be equal to a third, right? 7/21ths is 1/3 once you do the cancellation, right? So that means that 7/20ths is bigger than a third, but 8/24ths is equal to a third. So that means we're going to have the order 13/40ths, 8/24ths, and then 7/20ths, because 7/21ths is equal to a third, and that's 7/21ths right there, right? Because 8/24ths is equal to a third also. So that's how we can get that order right there. Okay, so this is the type of reasoning that we're trying to develop in our students, and we're trying to develop in you right now, actually. So again, try to avoid using calculators. It's okay if you get stuck. It's okay if you get stuck. Let the tension and discomfort just wash right through you, and you'll come out of it okay. Trust me, I've been there and I'll be here. All right. So let's try this. I want you to try to do this with your group or on your own at home. I just want you to indicate whether each of the following fractions are closest to 0, a half, or 1. So we're just looking about those benchmarks. So think about the number line and think about these problems and then write some answers down. Go ahead and take a few minutes to do that right now. Okay, now let's do them together. So 3/8. Let's think about a number line. I'm going to draw my number line up here. There we go. Here's 0, here's 1, here's 1/2. Now 3/8, I would be able to locate 3/8 if I took this whole unit and cut it up into 8 pieces and then marked 3 of them. Well, 4/8 is the same as 1/2, so 3/8 has got to be right about here. So 3/8 is definitely closer to a half. Okay, what about 5/4? 5/4 is bigger than 1, so it's got to be closest to 1. What about 2/9? Now, be wary here because you can't reduce 2/9. 2/9 is not the same as 1/3. Be careful about that. It's very tempting to do it because you're just like, oh, it's 1/3, so close to. It seems like it's 1/3 because the numerals are playing tricks on you, right? Don't rely on the numerals. Think about this. Think about what a ninth looks like and think about what 2 of them look like. Now, 1/9 is pretty small. 1/9 is if I took this whole line and cut it up into 9 pieces and only took 2 of them. So I'm definitely going to be pretty far down here. And what's even better is this, and this is why we like these things. 1/2, you ready for this, is the same as 4.5 ninths. Whoa, yeah, that's right. Yeah, you can use that. You can use decimals and fractions. That's totally fine. These are just numbers. Remember, they're just numbers. They're just representations of the number. I'm sorry, these symbols are representations of the numbers that we care about. And 4.5 ninths is exactly 1/2 because 4.5 is half of 9. So this is 1/2. So we know right away that 1/2 is 4.5 ninths, and we're looking at 2 ninths. So what is it? Is 2 ninths closer to a half, or is it closer to 0? And we can see that it's definitely closer to 0, because in order to get to a half, you would have to go up 2.5 ninths to get to 1/2. That's the idea. So it's 2.5 ninths away from a half, but it's only 2 ninths away from 0. So it's closer to 0. That's the idea. Okay, let's see. 4/7, we can kind of use a similar argument there. Let me delete this. So for 4/7, think about this. 3.5 is a half. Boom. So it's bigger than a half, and it's pretty close to a half, actually. It's only a half of a seventh away. So this is definitely closer to, oh, what did we say? 1/2, 1, 0. This is closest to a half. There we go. Okay, let's skip over and do some other ones. You can do 7/11 and 1/3. Let's go to something like this. What about 4/9? Actually, that one we know is very close to 1/2, right? Because 4.5 ninths is 1/2. So it's closest to a half. What about this one? 21/45. Let's think about that. Hmm, hmm, Well, I'm going to use the same technique again. I keep thinking about these halves, right? So 22.5 over 45 is 1/2. 22.5 45ths is a half because that's half of 45, right? So this is only 1.5 45ths away from a half. That's definitely close to a half, right? And now let's look at the next one, number 10. 13/15, definitely closest to 1. It's only 2/15 away from 1, so that's closest to 1. And then 13/84, actually, I'll leave that one for you to try too. Try these and see if you can make sense of them. Just remember to think of this number line and don't use a calculator. And don't convert it to a decimal either. See, that's another thing that students want to do. Students, they look at the fraction and they say, oh, turn it into a decimal and then compare everything. But you don't want to do that because that's avoiding fractions. You're explicitly running away from the representation using fractions to the safety of the decimal representation because you know that very well from earlier, right? You don't want to do that. The goal here is to get comfortable with fractions, to wrap yourself up in them and snuggle them and learn to love them, right? That's the idea. Don't push them away. That's not how you bring them closer, right? So here are some Common Core standards for students that are exiting grade 3. So if they're exiting grade 3, there we go, exiting grade 3, they need to understand this. They need to understand that 1 over b is the quantity formed by one part when a whole is partitioned into b equal parts. That's the partitive representation. And this is the big one. Remember this. Understand a fraction ab as the quantity formed by a parts of size 1 over b. Third grade. When you leave third grade, you should understand what that means. Third grade again. Understand a fraction as a number on the number line. They should be able to locate those things visibly and say like, oh, that's where it goes. And then represent fractions on a number line diagram, just like we were doing a little bit ago. Explain equivalence of fractions in special cases and compare fractions by reasoning about their size. Actually, again, compare fractions by reasoning about their size. Notice it doesn't say convert everything to decimal and then put them in order. That's not knowledge, right? That's not the skill they're supposed to leave third grade with. Just some restrictions here. In grade 3, the only fractions we really give students are fractions that have the denominators 2, 3, 4, 6, and 8, because those are nice numbers, right? Also, remember the manipulatives that we're using, right? You'll see when we get to chapter 7 that these pattern blocks lend themselves well to certain denominators and not others, as you'll see. But we'll talk about that in the next chapter. Um, by grade 4, we start giving them more denominators, and then in grade 5, there are no restrictions. So in grade 5, we give them anything. In grade 5, we give them all of this stuff. So by the end of grade 5, a student should be very, very comfortable with all numbers, all fractions of all types by the end of grade 5. Notice that it takes like 3 years to get very comfortable with these things. So we start them very early on and we give them 3 years of education in how to manage and deal with fractions, right? But if you teach your students to run away from the fractions, they'll never bring them to themselves, right? They'll never give them a big hug. Okay, where we are, yeah, okay, so let's pause again for a minute here and do some thinking. I'm going to ask you what quantities are represented in these 3 drawings, okay? So just take a moment and think about that. Okay, now let's talk about it together. So you can see that in this one, the first picture here, the rectangle is cut up into 4 equal-sized parts. So each one of those little rectangles is a fourth, and we're highlighting 3 of them. So if it's cut up into fourths and we're taking 3 of them, this is the quantity 3/4. Now let's compare that to the second picture. In the second picture, the rectangle is being cut up into 8 equal-sized parts, and we're taking 6 of them. So that is representing the quantity 6/8. And then in the last picture, we're taking the rectangle and we're cutting it up into, what is that, 12 equal parts, and we're taking 9 of them. So we're doing 9/12. So what do you recognize about the area shaded in each of these pictures? Think about that for just a minute. What do you recognize about the area shaded? That's right. It's the same area in each picture. Notice the area that is shaded does not change depending on what picture you're looking at. This is all the same area. So what that means is that these are all the same number. The shaded area is representing the same quantity, and consequently, these numbers are all the same number. They're all equal. And this is exactly how we explain what equivalent fractions are to students, exactly with pictures like this. These are equivalent fractions. 3/4 is 6/8, and 6/8 is 9/12. They are the same. They are the same, and that number is no different. But that's the catch, right? Fractions that look different numerically can refer to the same quantity. Well, what? 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 How is this possible? Well, it's not that far-fetched if you remember that we're talking about numbers and not just numerals, right? So that's why we spent so much time back in chapter 2 talking about the difference between numbers and numerals. So once you recognize that these numerals are just representing numbers, it makes sense that you can have different looking numerals to represent the same quantity. But that's a cognitive leap that our students have to make. They have to understand that. So fractions that look different can refer to the same quantity. So for example, these numerals, 2/3 and 100/150ths, they look very different, but they're the same number. That's because these are equivalent or equal fractions. So what I want you to try at home now is I want you to try to draw pictures that represent, or that show that 5/6 is equal to 10/12, which is equal to 15/18. So go ahead and think about that for a moment, how you would draw that. Okay, and now try to draw it out. Draw it out and basically try to emulate this picture right there. Try to emulate that picture. All right, let's move along. Okay. So this is the technical algebraic reason why those two numbers are the same. So let's just walk through it once. 3/4 is the same as 3/4 times 1 because any number multiplied by 1 is equal to itself. Why is that? Well, we're taking 3/4 one time. So 3/4 one time is 3/4. Done. Now, we can also say this. 1 is equal to 2/2. We're going to talk about this later, actually, but we'll do it now. Why is 2 over 2 equal to 1? Who says? Why? You just going to take my word for it? No, don't do that. Why is 2 over 2 equal to 1? Well, what does this symbol mean? Remember? The meaning of A over B. It's how many times does B fit inside of A? Well, how many times does 2 fit inside of 2? Once. It fits in there once. So what that tells us is that 2 over 2 is equal to 1. That's equal to 1. That's why, by definition of division, essentially, right? By the definition of that symbol representing a fraction. Okay, and now we can multiply these, and we're going to get 3 times 2 in the top and 4 times 2 in the bottom, which is 6/8. So why are we allowed to do that, do you think? Huh, interesting. Well, I encourage you to look back at these pictures and think about that. And you also should have noticed something similar when you did this at home, and then notice that it was a little trickier when you tried to do this. So think about that. And we can talk about it some more in the collaboration meeting too. So this property is an extremely important property because it shows that a common factor of both the numerator and the denominator can be quote unquote ignored, okay? This is what cancellation really is, removing factors that are equivalent to 1. And I think this is where we have this conversation. Oh, there you go. Why is A over A equal to 1? We just talked about that. But I want to talk about cancellation for a minute here, because another issue that I notice students carry over, or it's somehow they pick this up at an early age and they keep doing it. You can only ever cancel factors. You cannot cancel terms. And I'll give you an example here. And this is why we talked about this in the previous lecture, because students often think you can cancel terms, but you never can. The only reason that cancellation works is because of this, this right here. Actually, let me say this. Let me highlight this. If you can factor the numerator into something like this and factor the denominator into something like this, and you have a common factor in both, then you can essentially pull those common factors out like so, and that's just equal to 1. And anything times 1 is just equal to itself. That's what cancellation is, where you do the like slashing thing. That's like the best part. You know, it's like the best part of algebra, being like slash, 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 slash. It's so fun to like cancel a bunch of stuff. But what is cancellation? It's that. So here's the example I like to give, because this is where students start to go down the dark path. Let's look at this expression here. And I'll ask you to pause and think for a moment in just a second. Let's look at, let's do this. Here's my question. If I write x plus 5 over over 5, the question is, can you cancel those 5s? Can you cancel those 5s? Think about it for a minute. Can I do this? Well, the answer is no. No, you cannot do that. And it's an illegal maneuver, you could say, because that's not what cancellation is. Doing that is not at all encompassing what's going on down here. This is what cancellation is. So if you're ever wondering if you can cancel, the answer is no, unless you can do exactly what you see down here for the numbers that you're working with. So by comparison, take a look at this. What if instead I had this written? Oops. Now my question is, can you cancel those 5s? What do you think? That's right. The answer in this case is yes. Yes, you can cancel those 5s. But why? But why? You should be able to prove it. You should be able to verify that you can, and we're going to do that right now. Watch. I can use the distributive property and factor out a factor of 5 in the denominator, or in the numerator. And now I have a factor of 5 in the numerator and a factor of 5 in the denominator. So I can basically write it like this. Oh, I shouldn't use x and x, right? I'll just write it like this. Okay, so 5 over 5, that's just equal to 1. 5 over 5 is equal to 1, so this is equal to x plus 1 right there. Okay, I can hear my daughter in the background. Oh yeah, so this is what cancellation actually is. Cancellation is being able to do this. So if you can't factor out that factor in the numerator, or should say, yeah, factor out that factor in the numerator and in the denominator, then you can't cancel. So when I teach intermediate algebra and when I teach children, I never ever just go straight from there to there. I would never do that because then what happens is students start canceling everything. They start seeing terms that just happen to look similar and they're just like shwa 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 shwa. No, bad news bears, right? So don't cancel unless you can explicitly do this right here. Okay, we talked about that. All right, so some definitions here. A fraction for which the numerator and denominator share no common factors is written in lowest terms. So you might often hear write this fraction in lowest terms or fully reduce this fraction, et cetera, et cetera. A prime number, we've already talked about this, right? We know what primes are from chapter 11. We know what greatest common factors are and greatest common divisors are from chapter 11. We know what relative primeness is from chapter 11. And we talked about relative primeness. We also know what a least common multiple is. And this is like the first new definition, but it's equivalent to something we already know. The least common denominator of two or more fractions is the least common multiple of the denominators. That's what it is. So yeah, there we go. So the reason that I pulled chapter 11 forward is because for us, we're more mature, we're more mathematically advanced, and we can use those more technical ideas to help us work with fractions, okay? But for children, the stuff that we learned about in chapter 11 is too complex, right? So how can we explain to children how to find least common multiples? Well, what we do is we just have them list all of the multiples. And this is a good practice because they don't know the multiples yet. They don't know multiples. So when you're talking about this, you tell them to just write the list, just like this. Oh, sorry, just like this. Write the list. And the least common multiple is the first time, actually, I don't want to use red for that, pink, is the first time the lists agree. Now, there may be many, many more times that the list agrees, and those are just common multiples. But this is the least common multiple. Oh, anyway, so and again, you can see they can keep writing. This helps them practice learning what the multiples are. All right, so now let's talk about how we can relate fractions, decimals, and percents. Excuse me. So this is from the book. When children were in a research study were asked to find the sum 5 plus 0.5 plus 1/2, many said that it could not be done because they thought, that should say thought, because they thought fractions and decimals could not be combined. Uh, that's not correct, right? And the reason is because they're not comfortable with these as numbers. They're locked on the numeric representation. They see this as a number and they see this as some different number, some other type of number in some other world or whatever. And they just see this as like a fraction. So they think that the structure of the representation is the number itself. But that's not correct, right? And we've been talking about that for the whole semester. Um, so that's a big problem. And we don't want students to feel that way. We want them to recognize that these are numbers no matter how they look. So first of all fractions, and by fractions in this context, I mean rational numbers. We'll talk about that more in chapter 10, chapter 10, that way. All fractions can be represented as decimals, all of them, all rational numbers, sorry. Many decimals can be represented as fractions, but not all. But not all. So keep that in mind. Just because you have a decimal representation does not mean that you can write it as a fraction. So keep that in mind, or a rational number, I should say. But both fractions and decimals can be represented as percents. So percents are super nice. They work with anything, fractions, decimals, whatever. So let's do this. Let's write the following expressions as percents. But before we do that, let's make sense of what a percent really, really is. So what does that word mean? What is this symbol? That symbol, right? That symbol means percent. And when you're trying to figure out what a percent is, just think about the word, okay? The word is percent. Now, where else do you hear the word cent in life? You're probably thinking, oh yeah, dollars, right? Yeah. How many cents are in a dollar? 100. 100. Let me ask you this. How many years are in a century? 100. That's right. There's 100 years in a century. What else? Oh, when a country celebrates its centennial, it's celebrating its 100th year anniversary, right? So cent means 100. It means 100. And per literally means per. It basically means a fraction bar. So a percent quite literally means per hundred. Literally means per hundred. So if you say 5%, this is 5%. It's 5 per hundred. 5 per hundred. Sorry, I was trying to say 5 per hundred. That's the idea. So that's what a percent is. All right, so now let's try to do these things over here. Oh, all right, so 3/4. What percent is that? Well, I just need to get a 100 in the denominator. If I can get a 100 in the denominator, I'll know how much percent that is. And in this case, it's going to be 75 over 100, which is 75%. There you go, 75%. I think everybody knows a half, right? That's 50%. Why is that? Because if I get the denominator to be 100, the numerator is going to be 50. And then what about this one? 0.37. What percent is that? Well, remember from chapter 2, this is 37 hundredths because that number 37 ends in the hundredths place. So that's 37 hundredths. But 37 hundredths is the same as 37%. So it's 37%. How about this one? Now, we're going to use the same reasoning we just did. This is 145 hundredths because that number 145 ends in the hundredths place. And 145 hundredths is, guess what? Oops. 145%. There it is. And you can proceed this way. What about this one? This one's interesting because in this case, it doesn't end in the hundredths place. It ends in the thousandths place. So this is not even a whole percent, right? Or I'll say this. It's 2.8 hundredths, right? So that it's 2.8 hundredths because it's two whole hundredths and then 0.8 of another hundredth, right? You might even think about writing it like so. It is 2 hundredths plus 8 thousandths. But what's 8 thousandths if you write it as hundredths? That's the same thing as 2 hundredths plus 0.8 hundredths. So it's 2.8 hundredths. And 2.8 hundredths is 2.8%. There we go. That's the idea. I'll let you try to do number 6 on your own. It's similar, but that's the idea. And we can do more in the collaboration meeting if you'd like. Actually, here, right now, at home, I want you to try these ones on your own and with your group, right? So try to write these following percents as decimals and as fractions. Try that for just a minute here, and we'll talk about a couple of them. All right, now try to write something down. All right, now let's talk about it. Let's see, 32% as a decimal and as a fraction. Well, this is going to be nice actually because 32% is literally 32 per 100. And that's 32 hundredths, which means this is 0.32 because it's 0.32, it's 32 hundredths. Over here, this is 123%, so that's 123 hundredths, or in other words, 1.23. How about this one? Give myself some space. 0.01% is 0.01 hundredths. How could I write that as a fraction without a decimal in it, though? Well, you know what I'm going to do? I'm going to be clever. We can do this. This right here in the top, the numerator is 1/100th. So I'm going to write it like this. 1/100th. So it's 1/100th of a percent. 1/100th of a percent. So we can rewrite this as 1/10,000th. So that's it as a fraction. Now as a decimal, it's 1/10,000th. So it's going to be 0.0001. There we go. All right, and then like I said, I'll leave that one for you to try out, but the idea is the same. Okay, so now here's the question. Can every fraction be represented as a decimal? What do you think? Well, the way that we can convert a fraction to a decimal, well, there's a lot of ways we can. If you're unable to, well, let's try a couple of these, or you try a couple of these at home. Just try to use a division algorithm first. Try to use the standard division algorithm or the expanded algorithm, and try to write these as a decimal equivalent, all right? I'll give you a few minutes, so try that out. Think about it and write something down. Okay, now let's work on this together. So 2/5 is not too bad. 2/5, I can write that one as a decimal because I can think about it like this. This is the same as 4/10, which is 0.4. That's nice, right? That's pretty nice. What about 2/40? Well, I could try to do some division algorithm. You all might remember doing it something like this, right? You're going to take, oops, 40 and put it here, and then you have to put all these extra decimal places, right? We're going to do this in a moment here, but this is how you would set up that problem. Um, but again, we can be a little more clever, right? We can reduce this fraction. This is the same as 1/20th. And now here's where I'm going to get a little bit extra clever. 1/20th is the same as 1/2 of 1/10, right? When you multiply fractions, you just multiply across. 1/2 of a tenth. Well, what's 1/2 of a tenth? That's the same as, well, I'll say this. It's 1/2 of this thing. It's 1/2 of that thing. So if you want to have 1/2 of that thing, you're going to have that. Because if you add 0.05 and 0.05, you get 0.1. So 2.05s is 0.1. So that's 0.05. There you go. There's other ways you can do it too. Like I said, this is just one way to do it. Now, what about 1/7? That one, I can't really think about how to get it just by some manipulation like this. Let's go to the division algorithm. Okay, we're going to do this, and we're going to need a bunch of decimals, or a bunch of decimal places here to fill this out. Okay, so I'm going to use the standard algorithm just for speed here. Okay, so it goes 1, 7, 3, 0, right? Bring that down. Okay, it goes in there how many times? 4 times. We get 28, 2, 0. It goes in there twice. 14, 6. Bring that down. How many times does 7 go into 60? Not even how many times. We have to know exactly how many times. Let's see, 49, 56. So it's 8 times. Get 4. How many times does it go into 40? 28, 35 is 7 times 5. So we get a 5, we get a 35. I'm going to go over here now. We're going to have 5, bring down a 0. How many times does it go into 50? 7. 7 times to give us 49. Then we're going to get 1, bring down a 0. It goes in there once. Right, 0 goes in there once. Oh yeah, there we go. There we go. 3, bring down a 0, and then it goes in there 4 times. And now you can kind of see that there's a repeating pattern, right? 14, goes in there twice, dot, dot, dot. So in this case, what's happening is the pattern is repeating itself. And it starts repeating right here. So in this case, what we would do is we would actually write a bar over the repeating part of the decimal. So we'll put a leading 0 there just to indicate there are no units. Put our decimal point there. And then we're going to put a bar over the part that repeats, and only the part that repeats. Right there. And then we can erase the rest of this. So that is the answer, because what this means, this bar means that it's going to keep going that way forever, and that's the repeating block. It's going to go 1428557, 1428557, 1428557, on and on and on. So that's the answer. So that's how you write it as a decimal. Now I'll leave the last two for you to try, and then we'll talk about it some more in a moment here, and we'll talk about it in the collaboration meetings. Okay, So which ones did not terminate? Well, we definitely saw that this one did not terminate. So 1/7 is a decimal representation that goes on forever. It goes on forever. It might repeat, but it goes on forever. You can keep doing that algorithm until the whole of your life and beyond, right? So that one did not terminate. Maybe one of these two won't terminate also. You'll have to find out on your own. So here's the deal. This is the deal right now. When the denominator is a power of 10, converting to a fraction, or sorry, changing a fraction to a decimal is very straightforward, as long as you have a power of 10 for a denominator. And here's the catch. Any power of 10 can be written as a product of 2's and 5's. And we actually saw this in a previous lecture from chapter 11, right? Any power of 10 can be written as 2's and 5's, a product of 2's and 5's. So this is the big thing, nota bene, which means note well in Italian. When a denominator has only factors of 2's and 5's, okay? When a denominator is only has factors of 2's and 5's, then we can rewrite the fraction so that it has an equal number of 2's and 5's in the denominator. And that's what we're going to do, and I'll show you an example. So 7/40ths. Now, what I did was I found the prime factorization of 40, which we can do now from chapter 11. And that prime factorization is 8 times 5. I'm sorry, a factorization is 8 times 5, which is 2 cubed times 5. And that's the prime factorization. So notice here that the denominator only has 2's and 5's, right? Only has 2's and 5's in its factorization. So what that means is that we can get the same number of 2's and 5's in the bottom. And that's what's going on down here. There are 3 2's, there are 3 2's and only 1 5 there. But so what we're going to do is we're going to multiply by a clever 1, 5 squared over 5 squared. And then these are going to combine, these down here are going to combine to give you 5 cubed. All right, then, come here, erase that. All right, so then we're going to have 2 cubed times 5 cubed. Let me do this little calculation down here. 2 cubed times 5 cubed is 2 times 5 cubed, which is 10 cubed, which is 1,000. So that's right there. And then on the top, we have 7 times 5 squared, 7 times 25, which is 175. So the nice thing about this is that we can now write this as a decimal very, very easily because the denominator is now a power of 10. So we can just say that it's that many of those things, right? Because of our numeration system. So it's 0.175. All right. So in general, a fraction of this type in lowest terms, so fully reduced, will have a terminating decimal representation if the denominator contains only factors of 2 and 5. So let me emphasize that here. It'll terminate if there are only factors 2 and 5 in the denominator. If you have other factors besides 2 and 5, it's not going to terminate. It's going to go on forever and ever and ever and ever. All right. Oh yeah. Okay. So okay. If it goes on forever, then what are the possibilities? So if you have a fraction in reduced form and it's non-terminating, wait, hold on. I lost my train of thought here. It'll terminate if it's only got 2's and 5's. In general, a fraction of this form in lowest terms can be represented with a non-terminating repeating decimal if the denominator contains factors other than 2's or 5's. So basically, if it has factors other than 2 or 5, like I was saying, it's not gonna terminate. It's gonna go on forever, and it's gonna be repeating. It's gonna be a repeating decimal. Okay. Non-terminating repeating decimals, like those obtained from 1/7 or 3/11, are abbreviated by putting a bar over the repeating part. Bar over the repeating part only. And you have to pay close attention to that on the activity, on the assessments, on the WebAssign homework, because the bar is telling you what repeats. And we're going to focus on that in just a moment here. So for example, notice that the 7 here does not repeat. And that's why the 7 here is not included under that bar. Okay, so how do we go from decimals to fractions? So in other words, if I give you a non-terminating repeating decimal representation, like maybe I give you this, 1, 2, 3, How would you write that as a fraction? How do you go from that decimal to that fraction? How would you do it? All right, so here's how we're going to do this. We're going to learn this technique. There are other techniques that you can find online. There are all sorts of little tricks for these, but I would recommend making sure that you understand this type of argument, because this type of argument, how do I put it? Well, I'll show you. It's a little bit technical, but I'll show you. So first, from the past, we know that this is 1/3. So this is how you write 1/3 as a decimal. And actually, this is where I want to emphasize that 0.3 is not 1/3. Okay, so don't abbreviate or don't round, don't truncate. If you're talking about 1/3, then you either write it like this, or you write it like this, or you write it like this. You do not write it like that. That is not 1/3, that's 3/10. That's 3/10. It's not 1/3. It's kind of close to 1/3, but it's not the same. So don't make that mistake. All right, what we know is that we can write 1/3 in this way. That's 1/3, okay? And now from that, we can get we can get this. Or maybe I'll ask you to do this. Use this result to find a fraction for 0.1. So try to do this on your own. Think about it and write something down. All right, so how could we do it? Well, check this out. If this is 0.33333, and we know that that's equal to 0.3, and we divide both sides of that equation by 3, then we're going to get this. So this is handy, because 0.1 repeating is a very handy benchmark, as you're going to see. We're going to use this to build everything. All right, so let me ask you this then. What is a fraction for 0.7777777 repeating? And what's a fraction for 0.444444444 repeating? Think about it and try writing something down. Okay, now let's try this out. Let's see, if I know that this is 0.1 repeating, and I know that 0.3 repeating is 1/3, we didn't find the fraction for this. We got to go back. What's a fraction for 0.1? Oh, well, check this out. How did I get from 0.3 to 0.1? I divided by 3. What do I get if I divide 1/3 by 3? 1/9. This is the key. That's what I was trying to get at. This is the key right here. This is 1/9. There we go. So 0.1 repeating is 1/9. Sweet. This is our benchmark. This is exactly what we're going to use, okay? So 0.1 repeating is 1/9. Now, let's find a fraction for 0.7 repeating. Well, 0.7 repeating is like having 7 of those 0.1s, right? It's like you multiply, it's like having 7.1 repeatings, if that makes any sense. So all we need to do is multiply 7 times 0.1 repeating, and that's going to be 0.7 repeating. But this is 1/9. So this is 7/9. And that's as easy as it is. That's all it is. So 0.7 repeating is 7/9. What do you think 0.4 repeating is going to be? 4/9. That's right. So that's it. 0.4 repeating is 4/9. Okay. Now let's find fractions for 9.7 repeating and 0.004 repeating. So you try that. How would you find fractions for that? For those. All right, let's talk about it. Well, I know that 0.7 repeating, this guy, is 7/9. So I can write 9.7 repeating as 9 plus 7/9. Or better yet, I'll put the intermediate step, 0.7 repeating. So I'm just using our numeration system again, right? Our decimal system, and breaking things up into units and then the rest. So 9 plus 0.7, that's 9 plus 7/9. And then you can add those up by multiplying, finding a common denominator, and adding, right? So this is going to be 81 plus 7 over 9, which is 88 over 9. There we go. So that's 88 ninths. Not too bad, right? Now let's try to do this one over here. So this one's a little bit different. Notice that it doesn't start repeating until after that 0.0, right? But I know that this part right here, I know this. I know 0.4 repeating from the previous part is equal to 4 ninths. And this right here is equal to 0.04 repeating. So the only difference between this and this, and this is that it's shifted over by 1. Shifted over by 1, right? So what does it mean to shift by a decimal place? That's one of those Common Core standards, right? That you're supposed to leave, I think, 3rd grade with. We talked about it earlier, right? So what does it really mean when you shift? Well, in this case, it's dividing by 10, or better yet, multiplying by 1/10. So that tells me that 0.04 repeating is the same as 1/10 times 0.4 repeating. But that's equal to 1/10 times 4 ninths, which is 4 90ths. And that's the answer, 4 90ths right there. And that's how you do it. Pretty cool, huh? I think that's pretty cool. Okay. All right. Oh yeah, so we used repeated reasoning to find how to represent decimals with one repeating digit as a fraction. But what if the repeating block is 2 digits long, or 3, or any finite length, right? You notice how here it was like 1 digit, 1 digit, 1 digit, 1 digit, 1 digit. What if it's like 2 digits? What if it's like 171717171717, or 142875, 142875, 142875? How do I write that as a fraction? How do I go that way? So this is where things are going to get a little bit technical, but it's interesting. So first, recall that that is 1/9. 0.1 repeating is 1/9. Then here's what we're going to do. We can write this like so, and this is going to get a little bit weird, so let me try to explain this here. This part is clear. 1/9 times 11 over 11 is 11 99ths, and 11 over 11 is 1, so these are all equal, right? This is equal to this, which is equal to this. But what is 11 99ths? 11 99ths by definition is 1 99th 11 times. It's 1 99th 11 times. And this is what we're going to leverage right now, all right? So this actually implies that 1 99th is equal to 0.010101010101, or in other words, 0.01 repeating. Now, I claim that that's true, so I should probably explain why that's true, and that's why this little hint is, that's why there's this hint right here. So let's take the hint and see if we can make sense of this. What if we repeatedly add 0.010101010101? What do we get? Let's find out. Okay, so 0.0101010101. If I add that to itself, I'm going to get 0.02020202 ... And then if I add, so that was one time, right? I added it once. What if I do it again? 1, 1, 1, 1. I'm going to get 0.03030303. And what if I keep doing that, right? Well, you can kind of guess where this is going. Let's look at what happens after when I get to 9. If I do this 9 times, then what I'm going to get is 0.090 090909 ... And then what if I add it one more time? If I add 0.01010101, well, when I add 1 to 9, I get 10. So we're going to have a rollover, right? And we're going to have 0.10101010, right? So now I've added 0.01010101 10 times. What do I get when I add it one more time? Well, now I'm going to get 0.11111111, which we know is 1/9. There we go. So that tells us right here that 1 99th right? 1/99th is 0.01 repeating, because if you add that to itself 11 times, you get 1/9. There you go. 199. 1/99th. Pretty cool, huh? Okay, so long story short, this is the takeaway from that. The takeaway from that is that 1/99th is equal to 0.01 repeating. And that's handy because that lets us shift within the repeating pattern. We're going to leverage this. We're going to do that right now. So check this out. 0.37, for example, or sorry, 0.37 repeating is the same as 37 times 0.01 repeating. But we know that that's equal to 37 times 1/99th. So it's 37 over 99. Pretty sweet, huh? I think that's pretty sweet. Okay. Or for example, here, you can just keep going, right? So basically the number of nines in the denominator is how long your repeating block is. So if the repeating block is 1 digit, it's 1 9. If it's 2 digits, it's 2 nines. If it's 10 digits, then it's 10 nines. And then you have the numerator, which is whatever was under the repeating bar. That's the idea. So the reason that actually works is because of this argument right here. So it's good to make sense of that at some point in your life. All right. Oh yeah, so how about this? Now we can start to combine things, and this is what you'll do on the activity. When you start to combine things, you can start to deal with stuff that looks like that. So that involves a shift and a repeating block of 3. So what you can do is break it apart in terms of the shift and then the repeating block. We can write the repeating block using our little trick that we just found out, and we can still keep the shift out here, and then we can apply that shift to the fraction. And there we go. That's what we get. All right. So yeah, you try at home, and we'll do like one of these, and then we're going to call it a day since we're pretty much near the end here. But yeah, you try it. Think about it and write some stuff down. Okay, let's try it. I'm gonna go for this one down here because this one is a trickier one. But notice here that the bar is only over the 8. It's only over the 8. It's not over the 0, right? So let's try to write this equivalently. This is 3 plus 0.08 repeating. Now, that's shifted down. That shifted down by 1 decimal place. So I can write this as 3 plus 1/10 times 0.8 repeating. But that's not too bad because we know that 0.8 repeating is 8/9. So we're going to get 3 plus 1/10 times 8/9, and that is 3 plus 8/90. And then now we can do common denominator and stuff, and we're going to get 278 over 90. And there it is. That is 3.08 repeating. And this is one of those times where if you don't believe it, you can try to do a division algorithm and see if it works, right? Yeah, so basically do something like this, 278. Okay, how many times does 90 go into 278? Well, it goes in there 3 times at least, and then it goes in there some fraction of a time, right? 270. And now you're asking how many times does 90 go into 8? And then you're going to get that it's this many times. Pretty nifty, right? All right. So some quick classification here. We're almost done. Notice that all the numbers we've been working with they either have a terminating decimal or a non-terminating repeating decimal. So it either ends or it repeats on out, right? Keeps repeating. Any fraction that has that behavior that either terminates or has that repeating block, that's called a rational number. So that's one of the ways that we can classify rational numbers. So a rational number is a ratio of 2 integers, not where the denominator is not 0. But that's all a rational number is. Rational numbers are like 2/3, 157, 2/38, 1, 2, 1, 8, 9 over 46. These are all rational numbers. So these fractions, when you convert them to a decimal, they will either terminate or they're going to repeat a chunk, right? That's a rational number. Now, not all numbers can be represented as a ratio of 2 integers. In other words, not all numbers have a terminating or not all numbers have a terminating or non-terminating and repeating decimal representation. And those are called irrational numbers. Irrational numbers. But we'll talk about that more later. Oh, sorry. Wait. Oh, that's at the end. Okay. Here are some irrational numbers, for example. Pi, square root of 2, square root of 3, e, the number e, irrationals. We'll talk about these in chapter 10, actually. Um, the set of real numbers, sorry, I lost my train of thought. Oh, yeah. So the set of rational numbers together with the set of irrational numbers forms the set of real numbers. So you take the rationals, you take the irrationals, throw them in a bowl, and you get the set of real numbers. Those are the ones that we deal with on our every day, right? But yeah, more on that later. We're going to focus on that later. Let's tie it up here. Last little bit, some issues for learning, understanding fractions and decimals. So you'll notice that learning to understand fractions is difficult, and this is like the longest lecture. I think it's probably the longest lecture of the course, actually. There's a lot of content here. There's a lot of stuff to make sense of. It's difficult to do. So embrace that and let your students know that that's okay. There are several critical ideas that learners need to understand before they can successfully operate on fractions. And this is the key. If students don't have these, then they can't do fractions very well. They can't work with them comfortably. So here we go. When breaking up a whole into parts, the more parts there are, the smaller each part is. So for example, actually, I'll just say this. This is the key, right? We actually used this earlier on in the lecture when we were comparing fractions. If students don't understand that 1/5 is larger than 1/6, they're not going to be able to operate with fractions. It's going to be real hard. They're going to be really upset. Um, yeah. So even though children might understand this in a particular setting, it's important that they make the transition to representations using symbols. So this is one of those times where I'm finally pointing out that students have to make that transition at some point, where they transition from the models and they move on to the symbols, right? We do need them to make that transition, and hopefully they've got a nice robust foundation so that transition is very comfortable and easy for them. They also need to understand this, that fractions represent a specific quantity symbolically. In other words, for example, this is one number. 3/5 is one number. Oftentimes students think that they're supposed to do things differently to the top and the bottom and all that, but that's not the case. They'll try to operate on the numerator and the denominator separately, and that's not correct. They need to recognize this as a number, a single number. It's purely a symbolic misconception. They really just don't understand how the symbols are representing the ideas. They don't understand the numeration system. Equivalence of fractions is critical, absolutely, as we saw. Students will not be able to add or subtract fractions unless they can generate and identify equivalent fractions in a comfortable way. So that means they need to understand multiples, they need to understand factors, they need to understand least common multiples, they need to understand greatest common factors. They need that background to work with fractions. And also, young learners must understand why like denominators are necessary before they can add or subtract. This is from the book. It says, only when there is a common denominator for two fractions are they adding or subtracting like pieces, because now both fractions refer to a common size for the pieces. That is a critical bit of understanding they need if they want to be able to do operations on fractions. And that's where we're headed. That's the next lecture, is operating. We haven't really been adding or subtracting or multiplying or dividing fractions that much. We've just been talking about what they are and how to represent them. Yeah, all right, so activity 6B, let's play. We can go take a look at that really quick. 1 second here. Yeah, 6B. All right, very similar. So write these expressions as percents. So convert those to percents. Convert these to decimals and fractions. Write these fractions as decimals. And find fraction equivalents for those decimals. These are the ones that are repeating, right? These are the ones that are repeating. So those are from actually the slide too, so you can work on those. All right, and that's it. So that's activity 6B. I think I'm going to go ahead and call it there. This is a long lecture. Thanks for bearing with it. You can take a break. one of the reasons I like to provide this asynchronicity is so that you have this time, you have some flexibility so that you don't have to watch this whole thing all at once if you don't want to. All right, so I guess that's it. I'll see you at the next lecture and I'll see you at the collaboration meeting.